Thank you very much, and thank you for the opportunity to present at this webinar. I'll now share my screen so everyone can see the presentation. And as mentioned, our initiative is really focused on turning waste plastic into sustainable green concrete. But before we go into the solution itself, I think it's worth spending some time on the problem statement that we're looking to address. When we talk about carbon footprints, sustainability can encompass many different aspects and many different elements of the problem. But in particular, I think it's worth looking at the macroeconomic problems that we will be facing globally and more acutely in Asia. Population growth is set to rise to close to 9 billion by estimates by 2050. Over 5 billion of those people will be living in Asia. And also populations are aging, which increases the burden on countries as the population grows. But another key problem will be the rise of urbanization, rural populations moving into urban centers, and hence driving the need for construction and the resources that go into construction, but also generating huge amounts of waste, which is a particular problem within large cities. And close to 6 billion, over 6 billion people will be living in cities or mega cities of 20 million plus populations in 2050 and beyond. I think this creates a huge strain on not only the building sector, but also the waste management sector. The plastic waste crisis, I think it doesn't bear too much repetition. We're all very familiar with regards to the plastic problem across the world, but again, focusing on Asia in particular, 80% of ocean plastics come from Asia, and that will continue to be a problem. But one particular problem which does not receive much publicity, which is of particular concern to the building sector, actually relates to raw ingredients for concrete, being sand. I mean, some people are aware, some people are not aware that it requires a particular type of sand for concrete manufacturing, and that's a diminishing resource. It takes hundreds of thousands of years to occur naturally. And with rampant urbanization, demand for construction, there is a finite supply which is getting smaller and smaller. And this actually led to a lot of unpublicized problems with regards to illegal mining across many Asian countries, which released the destruction of habitat, destructions of homes, communities, and even more adversely, people are killed in the process. There are sand mafias, there are journalists, politicians, policemen, local community leaders who have been injured or killed in the process of trying to protect their local environments from this illegal mining. So it's a hidden problem which I think will become more prominent as it becomes a more direct issue that we'll be faced with. So if we turn then to Hong Kong's problems in particular, which is something we're very focused on. Waste generation in Hong Kong, again, it's no surprise to anyone that there's a huge amount of waste generated in Hong Kong, and in particular plastic. As of 2018, I believe, just under 850,000 tons of plastic was sent to landfill. And the recycling rate has unfortunately been very low. And Hong Kong isn't alone in that particular problem. It's a global issue. Only between 7 and 8% of Hong Kong's plastic is actually recycled. As obviously we're discussing now, embodied carbon is a particular issue for the building sector and the construction sector. Whilst great strides have been made in reducing operational carbon, the challenge of embodied carbon is quite particular. It requires a very different mindset when it comes to the solutions. Hong Kong's got very limited local plastic recycling capacity. Historically, the plastic has been sent abroad, either in its raw format or semi-processed format. But for obvious reasons, it's very difficult to have scalable recycling solutions here in Hong Kong. But again, strides are being made in that regard. Unfortunately, many recycling options are not financially viable without some form of support or subsidization, or they're simply not scalable. Landfill capacity has been an issue and a problem for Hong Kong for many, many years and will continue to be so. Incineration of waste, unfortunately, is a plaster and a flawed one at that in terms of dealing with Hong Kong's waste, and leads to its own particular problems in terms of pollution. And as we see around us all the time in Hong Kong, there's a huge amount of construction going on, and the demand for raw materials as well as finished goods in terms of building materials is only set to increase. And as of 1st of January this year, the Basel Convention amendments made it even more difficult to move plastic waste across boundaries. So Hong Kong really has to look at solutions within its own borders in terms of dealing with waste plastic. So introducing the EcoBricks solution, in its very simplest form, it is a concrete paving brick. What we do is replace the sand and aggregates in that paving brick with waste plastic. We've successfully substituted up to 50% of the raw ingredient input with waste plastic. It's a fully Hong Kong circular economy solution. We take waste from Hong Kong, we manufacture the bricks in Hong Kong, and we will be selling the bricks for use within Hong Kong. I think that's important, and a lot of people question our sanity when it comes to manufacturing paving bricks in Hong Kong. But for us, the ability to say that we are a closed loop solution for Hong Kong is very, very important. It comes at a cost, it comes with particular difficulties, but I think if we're successful, we can prove that that can be done within Hong Kong's borders. We've indicatively calculated that our bricks can save up to 50% in embodied carbon. There's no perfect calculator out there at the moment. It's very much work in progress across the industry, but there's a significant saving in a local economy solution for turning waste plastic into concrete building materials right here in Hong Kong, as opposed to having them manufactured with raw natural ingredients in other countries and shipped in. The product itself is lighter than standard concrete products. As you would imagine, plastic is somewhat lighter than sand and aggregates in many cases. So transportation costs, carbon footprint from transporting it, the relatively short distances is reduced as a result of that. And as I mentioned, we can put a lot of plastic into each brick. In 1 square meter of paving, we can incorporate the equivalent of 1,500 plastic drinks bottles. So in terms of being able to take the huge volumes of waste that we have as a problem statement, we can turn that into a very real and applicable solution for Hong Kong. Oh, apologies. And just looking at some of the key attributes of our solution, I think the most important one and most beneficial one is we can use virtually any plastic. And that's where we believe our solution is very complementary to other existing recycling solutions in Hong Kong, in that we can take plastic waste that is either very, very hard or frankly impossible to recycle. We can take types 1 to 7, and the plastics do not have to be squeaky clean. They don't have to be intensely washed or processed. And more importantly, we can take those hybrid compound plastics, take the humble toothbrush as an example, and recycle that, whereas it's very difficult to do that in terms of separating those compound plastics for traditional recycling solutions. Just to give you some scope in terms of the impact we can have, if we take just 5% of that waste plastic that I mentioned before, we can cover 2.2 million square meters of paving in terms of the number of bricks we can produce with that. And I think that really should be I guess a shining example of what we can do in Hong Kong within the local economy and local waste supply system. The other benefit of our solution is that we do not heat or melt the plastic, which I think is very important, because that in itself uses energy, has a carbon footprint, and also has harmful emissions within it. There's no chemical processing of the plastic either. So it's a very scalable and easily to implement solution for Hong Kong. Our bricks are, as I said, concrete. They look the same as traditional concrete bricks. They feel the same, they perform the same, and we are in the process of having them tested to Hong Kong's civil engineering standards, so that we can show and evidence that they are on par with traditional products. And whilst we're starting with paving bricks, we're looking to expand the range of building materials that we manufacture with our solution. So with that, I will just say thank you, and I will invite any questions that you may have either now or later during the panel discussions. Thank you.
Thank you. Thank you so much for the introduction. Hi, everyone. My name is Koon Min from PEN United Concrete, and I'm based in Singapore. Today, I'm happy to be here to share with you materials and technology towards achieving net zero embodied carbon concrete. Okay, first I shall share a little bit about PEN United. So PEN United, we are leading a ready-mix company in Singapore, right? So over here, what you can see is a snapshot of our vertically integrated operations from a cement terminals in Singapore to the slag or GGBFS grinding plant in JB. And we also run a quarry in Indonesia, right? And all these materials are being delivered and supplied to Singapore, primarily for Singapore consumption. So in Singapore, we are producing roughly about more than 4 million cubic annually. We have also ready-mix business in Ho Chi Minh City, Vietnam, and also in Malaysia as well. So our world-class innovation center that produces more than 300 different types of concrete solutions, out of which 150 are green certified. We also house a team of R&D scientists, material scientists, and engineers. But more importantly, this is done through collaborations with our customers, institutions, as well as consultants. And what we hope to achieve is actually also to generate future revenue through product licensing in regional markets. And not only innovating concrete solutions, I would also like to share with you our digital advanced logistic management. And this is powered by our AIR Digital. AIR stands for Artificial Intelligence in Ready-Mix Concrete. So when you can see the photo over here in the slide, is actually our command center that is in Singapore that basically controls the supply chain, total supply chain solutions, right from the materials delivery and to the concrete batching plants, as well as supplying concrete to our customer sites. All this is done through our internal in-house team of IT specialists that develop these digital solutions. An overview of our circular economy that we hold on dearly, that we adopt in our concrete production. So to give you a very quick run through, basically when we talk about the sustainable or the raw materials part that comprises and concrete that comprises of cement, natural aggregates, energy, and admixture, we tend to look at the materials and try to ask ourselves, of all these materials, which one actually contribute to the largest or highest carbon footprint in concrete? And in concrete, I think most of you are already aware that cement has the highest carbon footprint. And then we start to ask ourselves, how can we actually replace this cement with a greener alternative? And how can we actually lower the proportion of cement through technology? And we also have to keep looking at what other types of waste when we generated through our concrete production, and how can we actually upcycle this waste into new products. And even through our product innovation, the sustainability and always the intention of driving down our low carbon footprint would be the pillar in designing these concrete products. And also not forgetting the digital process, right? And over here, you can see we have our electronic delivery orders, our air digital that I have mentioned a little bit, right? And also through this digital process, we aim to achieve lowering down our embodied carbon in our concrete products offering to the market. So here are some of the modules that are from our air digital. And these modules are actually offered to the market for ready-mix companies globally. And our latest addition to our technology that currently we are exploring is AIM, Artificial Intelligence for Mixing, right? So as you can see from the chart below, right? So basically it's an integrated artificial intelligence and IoT technology sensors that enables concrete workability to be monitored after leaving the batching plant right to the customers, right? So in short, before we actually adopt this technology, we have our concrete concrete in our batching plant that is actually monitored or rather tested by our concrete slump checkers and workability testers at the batching plants. And after the mixer truck has left the concrete batching plant, basically the workability in the mixer truck, there's no way that you can change or monitor the workability. And we all know that in built-up areas like Singapore and possibly also in Hong Kong, there's a lot of higher heavy traffic conditions, and there's a lot of unforeseen circumstances even at site. And so much so that when the mixer truck reaches the site, it may actually face unforeseen circumstances where the concrete actually loses the workability. So with this system, the AIM technology aims to achieve measuring and monitor and is able to adjust the workability when the concrete mixer truck leaves the batching plant, right? So it enables the workability to be adjusted during transit, and at the point of discharging the concrete, our customers will be able to enjoy the workability that they ask for. So over here, you can see a few important benefits of using this AIM technology that currently we are doing some prelim study. So we can see the quality part. We are trying to achieve a consistent concrete workability, even when the mixer truck is caught in a traffic jam, or even there's when the mixer truck faces unforeseen circumstances at the site. For example, concrete pump breakdown and whatsoever. So consistent concrete workability is achieved with this system. And also, when we talk about the energy, the productivity savings, we expected more loads that is carried by the mixer truck, and also less manpower needed for a concrete slump tester, and also the concrete workability checks at the batching plant. And last but not least, under the sustainability benefits, our prelim study shows that we are able to achieve a 5% cement savings, and also 15% reduction in our diesel consumption of our mixer trucks. And not forgetting the concrete waste in terms of rejection is also increased, or rather is decreased. The rejection rate is decreased, and we have achieved a prelim study achieved a 10 to 15% improvement in this area. And currently, this system we are also planning to market to the industry. And from digital, now let's come to the concrete solutions that we have provided for sustainability. And this is an overview of our smart cities and vision that we hope that with the different types of low carbon concrete, we are able to put in and to build smart cities in Singapore. And these are the various low carbon concrete in various different sectors, from aviation, healthcare, marine port, underground, water management, aesthetic, and as well as residential and commercial. With respect to that, I'm sure Hong Kong, you're not familiar to your high strength and super high strength concrete of grade more than 100, right? So yeah, so in Singapore, we have also supplied concrete to these various sectors in order to achieve a lower carbon footprint. And our R&D formulated mix design shows us that, you know, with a careful design and with introduction of technology, we are able to reduce our embodied carbon footprint, right? And prelim lab study shows that our concrete carbon footprint can go as low as a reduction of 90%, right? And this is done currently with a new technology in cement technology and also in carbon capture utilization technology, which I'm going to show and share with you later in my slides. Okay, so this is a slide that shows the carbon dioxide mineralization technology or carbon cure. Carbon cure technology that is a carbon cure is a clean tech company based in Canada, and over here you can see that this technology uses CO2 in concrete, and by doing so you are able to increase the compressive strength of concrete, and whereby we are able to reduce the cement and reducing the embodied carbon in our concrete. So carbon cure technology has been installed in more than 300 concrete patching plants, and till date, more than 6 million cubic of concrete is being taught with this carbon dioxide utilization technology. And also a thing to note, carbon cure is also funded by Breakthrough Energy Ventures, a $1 billion clean tech fund headed by Bill Gates, among some of the successful businessmen such as Jeff Bezos and Jack Ma. And also the latest investor in carbon cure is Amazon, right? Amazon, which has the Climate Pledge Fund, has also invested in carbon cure. All this is done with the aim of achieving and accelerate decarbonization effort. Now let us take a look at what is it happening when CO2 is being injected. So on the left of the slide, this red color, this is the CO2 pipe that is being inserted in our central mixer. So during the production and mixing of our ready mix concrete, when our cement, stone, and even sand, CO2, liquid CO2 is being injected during the mixing process. And on the right, you can see the chemical reaction that basically tells us that the calcium carbonate, nano calcium carbonate is being formed when the CO2 is being injected. Now let us take a closer look at the this nano calcium carbonate. So in this slide, basically it is a scanning electron microscope, and the sugar cube structure is actually the nano calcium carbonate form. And because of this, it actually forms a lot of seeding sites for hydration to occur, right? And a thing to note that when the CO2 is being converted into a nano calcium carbonate, it will become permanently embedded in the concrete. Now, it's very important to stress this point because when we actually introduced this technology in Singapore, we were asked that, you know, when the CO2 that is being injected during the concrete production, what will happen to the CO2 after the building reaches the end of life, right? So essentially, the CO2 after the demolition of the building made with this carbon cure concrete, the CO2 will not be released back to the atmosphere. Reason being that it has been transformed and chemically converted into a nano calcium mineral. So as I mentioned earlier, because of this introduction of a nano calcium carbonate, it has actually increases the concrete strength. And so it actually gives ready mix producers like us an excellent opportunity of reducing our embodied carbon in our products by reducing the cement as much as 5%. And some of the international endorsement you can see over here. So in Singapore, we were our product, carbon capture and utilization product, is achieving the highest 4-tick status under the Singapore Green Building Council, SGBP, which certify green products, green concrete products. So SGBC in Singapore actually started or created a new product category just to acknowledge the importance of this specialized carbon dioxide utilization product. And also in Singapore, these test reports were conducted to compare the normal concrete and carbon cure concrete. And an independent assessment by Nanyang Technology Universities, Professor Tan and Professor Yang did their own assessment on the comparison, and they concluded that the performance of that concrete made with CO2 and normal concrete, the performance is comparable. And over to the overseas part, carbon cure concrete has also gained the approval in Germany under the DIN EN 206 standard. So in Singapore, our concrete standards is also adoption of this Euro code, which we call it SSEN 206. And at the same time, carbon cure technology is also approved under this ASTM C494 Type S for specific admixture approval. And not only that, in the Calgary International Airport, as well as the Canadian specs, together with Hawaii, these few states actually legislate the use of CO2 in their concrete for their projects. Now, what does it mean? Basically, it means that whatever concrete that is being used in their project, a CO2 ingredient has to be included. Now, some of the project reference that we have supplied to from residential to infrastructure, and also in these Lindy gasification plant projects. And last but not least, also for the Sabana Jurong campus. So a wide application was used for this carbon cure concrete in Singapore. Now, this is what we envision for Singapore. With a PEN United low carbon concrete, we are able to achieve an embodied carbon savings of about 260 kilogram CO2 per meter cube. So in Singapore this year is projected to create a total concrete volume of 10 million cubic. So we like to envision the part that when all the concrete in Singapore is being converted to this low carbon concrete, we are able to save 2.6 billion kilogram of CO2, and that is equivalent to about 43 million trees planted in Singapore. And now I come to the last few slides, which this is a very important slide that I would really need your attention for the next few minutes. This slide is taken off from the Institution of Structural Engineering, which is the world's largest membership organization dedicated to structural engineering. Now, if you look at the blue color, this blue color is basically the embodied part of the embodied carbon, which I think the World Green Building Council named the A1 to A5 as the upfront carbon. So when you look at A1 to A3, essentially this portion creates 50% or represent a 50% of embodied carbon in the whole life carbon development of a building, of a life cycle. Whereas the operational carbon at B6 is only at 23%. So what's the thing that I'm trying to emphasize is that the part of the 50% is very crucial, especially during the planning stage. When consultants or even for builders, once the type of concrete has been decided, right, this embodied carbon that is built inside the building cannot be changed over the life cycle or the lifespan of a building, which is typically 70 to 80 years or even more. So this embodied carbon stays with the building. Whereas for operational carbon, we are still able to change the chiller, or probably can change the lightings into much energy efficient. So again, coming back, this 50% is a huge proportion of the embodied carbon, and that we are unable to change. So the planning part and the decision to use low embodied carbon is very crucial in this area. And that's why we need all stakeholders, to really take bold actions. And just like I mentioned, from developers, to consultants, or even for manufacturers, they have to get ready their low carbon solutions, which I believe the ready-mix companies in Hong Kong is already doing that by having GGBFS or even fly ash, in their product offering. So the next thing that we really need to change our mindset is to how can we actually spec this low carbon concrete in our products or even in our tender specification. And one area that we can look to is, or even that we can explore, is actually through the action by the government, and that is to consider having some financial incentives to use low carbon materials. And right now we are not only talking about concrete, we also like to even look at low carbon glass or even low carbon steel for that matter. We believe that having that kind of financial incentive will help to drive the market into accelerating the adoption of such low materials and even implementation of a low carbon technology. And moving on, this is the last slide that I feel that is a very good example from New York, that probably even for Singapore that we can even look to it and see how can we adopt the framework. So this is a LECCLA, it's a Low Embodied Carbon Concrete Leadership Act that the New York proposed to be legislated this year. And basically it encouraged the use of low embodied carbon, and the act actually encouraged developers, and when they use low carbon concrete, they will be placed at the highest priority to win projects if their concrete has the lowest carbon footprint. So I believe this is something that we can help to explore further. Okay, so with this, I thank you very much for your attention. And this is my contacts. Please feel free to contact us for any of these AIM or even a carbon cure product offering that we are more than happy to share. Thank you.
Good afternoon, everyone. And I'm CS POON. I'm from Hong Kong Polytechnic University. Today, I'm going to share with you some of the research that we have been doing at the university about using CO2 as a means of carbonation of concrete materials to achieve aim of recycling construction waste. Okay. So some of the statistics in Hong Kong, and the construction sector is the biggest consumer of materials, and is the second largest carbon footprint contributor in Hong Kong. And construction waste, okay, this is the number waste solid waste stream in Hong Kong. It's amounting to 50,000 to 60,000 tons per day. Okay, this is huge amount. And when compared to municipal solid waste, that is the waste that we generate from a household, from our offices, or from restaurants, which is only about 10,000 tons a day. Okay, but construction waste is about 50 to 60,000 tons a day. And we have estimated about 5% of this, 5 to 10% of this construction waste is concrete, waste concrete, demolition concrete, or waste concrete from construction industry. So it's amounting to about 3,000 to 6,000 tons per day. And on top of that, there are some concrete solid waste, which is generated from our abatement plant. There are also glass waste is generated in Hong Kong. But today we are going to focus on construction waste. Now, this is some of the research that we have been doing at the Polytechnic University under the theme of circular economy, or turning waste into eco-construction products, C&D waste research, waste glass research, and also incinerator ashes research. Okay, we have the TPAP, which burning sewage sludge every day and producing about a couple of hundred ashes a day. Okay, but we are going to have the IWMF integrated waste management facility. Okay, which will be commissioned in a few years' time. 2 to 3 years' time, we will be burning 3,000 tons of MSW a day, and it will generate about 600 tons of ashes, IBA and fly ash. So we have been working continuously in this front as well. And we have also been in Polytechnic, we have also working on timber and also waste tire and turning waste tire into, for example, blocks works or rubberized asphalt. But today we focus on construction waste. Construction waste are generated. We are talking about 50 million tons a year in Hong Kong. Is about 50 millions, and it generates from various activities, particularly from demolition or roadworks. Okay, we have resurfacing road, which is a concrete road. There's a lot of concrete waste, and so the concrete waste nowadays, the management is mostly collected. They are put into the public fields, and then the use of reclamations. Okay, and the reclamation is not the most beneficial use, I'm afraid. It's a low end, you record it, because waste concrete itself has some values. It can be turned to recycled aggregate after crushing, sorting, and removal of the contaminant. It could be used as a recycled aggregate, and this is what we are trying to do. Okay, you can see that is the flow chart of demolition waste. Okay, now demolition from a demolition site is collected and transported. If it is recycled, it will be going to a crushing operation. Okay, and then after crushing, sorting, it will be turned to a removal of contaminant. It will be changed to we call the recycled coarse aggregate, recycled fine aggregate, and also during the crushing operation, of course, there are powder generated. The powder are mostly cement powders. Okay, you can imagine. Okay, concrete itself is comprised of aggregates. Okay, and cement and mortar. And then after crushing, there are always very fine powder. And then in Hong Kong, through almost 2 decades of research, we have already developed some usage of this recycled coarse aggregate. Okay, coarse recycled aggregate can be used for concrete, can be used for paving materials, and then some of the blocks that been developed by the Polytechnic that we call EcoBricks have been using this as an aggregate to substitute natural aggregate. Okay, so what we have been doing and why we are interested in carbonation is the recycled aggregate itself after crushing. Okay, this is a schematic of a recycled aggregate. Okay, it's about you can visualize it as a 20 mm in diameter. Okay, there is the lateral aggregate. Okay, inside, and there is the mortar. Okay, old mortar from the old concrete, the old mortar, old cement paste, as well as sand covering the natural aggregate. If you dissolve this material, this is the before and after dissolving and exit. This is you can see the gray color. This is mainly cement paste. After dissolving and exit, the cement paste or the mortar has been removed, and then you can see the aggregate. Okay, so actually it's quite substantially amount of mortar is covering the old natural aggregate, and because of this attachment of the old mortar, this old mortar comparatively density wise and strength wise is inferior to that of the natural aggregate. For example, the density of this material of natural aggregate is 2.6. The density of mortar may be 2.2 or 2.3. And then that means the density is lower. That means it's higher porosity and easier and lower strength. Lower strength, and then making the system poorer or the whole thing poorer mechanically. So when we use this as receive, and then after crushing, and then sorting, and then sieving, to make recycled material, normally we'll end up with a lower strength. This is some of the research data, including ours, in published some years ago, POON et al., for example. And then you can see using this material to produce concrete or produce other material, you will normally have a 20% to 30% decrease in capacity strength or modulus. Okay, okay, that is why we need to devise method. Okay, this is the method we try to improve the recycled aggregate, including removing the old mortar. Removing the old mortar means removing the old cement paste, particularly, and this is developed in Japan. You can see Japanese name, and then mechanical grinding, ultrasonic cleansing, heating, of course, involving a lot of energy, or acid dissolving the old mortar, and also surface modification. And then this would try to remove the old mortar, that is the cement paste is separated from the natural aggregate. So the natural aggregate will be recycled, because we are now in terms of sustainability, the natural aggregate become more expensive or difficult to obtain. Okay, particularly like Hong Kong, we're using granite or river sand is natural aggregate. Okay, and there another process of enhancing the property of the recycled aggregate we call strengthening. Strengthening means going to back to this, because this is weaker. Okay, this is weaker, and then if we can strengthen this portion, we will make the whole system better. How do we strengthen it? By impregnation with cementitious slurry, or impregnation with a water glass, that is water glass, and also by a polymer. And then what we are very interested in Polytechnic University is by carbonation. Okay, carbonation. Carbonation by deposition of calcium carbonate in the layer. Okay, and then the carbonation can be done by CO2 and also be done by bacteria. Okay, and there's another method we call nanomaterial. We call a nanomaterial, nanosilica, for example. This is beyond the scope of today's lecture, but we have done a lot of research in this area as well, and then we are trying to commercialize this as well. So I'm sorry, this talk is a bit academic, because this is real science. Okay, involved. It's not about the university is not marketing anything. Okay, we try to produce science that can be used for the industry. So if you look into cement, okay, cement basically comprised of clinkers. The clinkers are tricalcium silicate, tricalcium aluminate, dicalcium silicate. These are the mineral phases in the cement. Okay, after you add water, there is hydration. Hydration will turn the clinker phases into the hydrates, calcium silicate hydrate, calcium hydroxide, or the etching gas. Okay, if you're in the concrete industry, you should know what I'm talking about. But okay, all these hydrated phases, or well as the unhydrated phase, can be carbonated under the right condition. When carbonation occurs, it will turn mainly into, as what Mr. Lim has said, okay, it will turn into calcium carbonate. But there's another, it's not so simple. Okay, the carbonation product, not only calcite, but there's also silica and also other materials. Okay, but with this carbonation process, there will be change of density, and there will be change in volumes. And by virtue of these changes, we try to densify. Okay, densify the old mortar. Okay, that's why this in here. Okay, we try to densify this mortar by carbonation. Okay, and then the material will be as good as natural aggregate. We hope. Okay, this is our wish. So this is basically the equation. Okay, okay, the hydration product in cement or in concrete is not the clinker phase already. It's the calcium silicate hydrate or calcium hydroxide. Okay, with the addition of CO2, and they will turn to calcite or calcium carbonate, and then there's some silica phases. And calcium hydroxide will be only turned to calcium carbonate. Okay. So this carbonation reaction actually occurs naturally. Okay, because if you're an engineer, you know that concrete corrode, and the corrosion is basically because of carbonation. Okay, concrete during the surface life is exposed to atmospheric CO2, and then this atmospheric CO2 will carbonate the concrete. Okay, very slowly because of the poor porosity. And this carbonation is not good, okay, for corrosion purpose because you will lower the pH of the concrete. But after the concrete is come to an end of life and demolished, this concrete element or structures will be crushed to small elements or small particles like the recycled aggregate. It will be exposed to, because it will have much higher surface area, it will be exposed to CO2. If you add a very high concentrated CO2 source here, for example, under accelerated carbonation scenario, meaning you are not using CO2 in the air. We are using CO2 from flue gas, from power plants, from cement plants, or from industry. Okay, then the cement plant or power plant contain 10 to 20% CO2. Okay, on average, and this CO2 will immediately carbonate the material very quickly, and then this material can be densified and turned to a much better recycled aggregate. And this recycled aggregate can also be turned into new construction products. Okay, so this is the concept. Okay, we have done a lot of experiment to optimize, because if you do it in atmospheric CO2, naturally it would take months or years to do it. But of course, we cannot wait for example, in a recycling plant, we cannot wait for too long. Okay. So we need to do it quick, and then that is why we do it by accelerated carbonation. And then there's certain conditions to be met in order to have an optimum carbonation, like the humidity. We have the right humidity, the right temperature, and so the right pressure. Okay, we are doing the right particle size of the material. If it's very big, of course, the carbonation is small. The smaller the particle, the better. The higher the carbonation rate. That is the empirical relationship that we developed at the PolyU, and that is published. If you're interested, you can look into our papers. And so we have developed this. Okay, so we, with the help of a concrete producer, we have done a very so we call it large-scale experiment. We have produced a new batch of concrete. Okay, a new batch of concrete. We call this new recycled aggregate. We produce it. We know exactly what they are, and the ingredient or constituent of concrete, and then we crush it. Okay, after a few months, we crush it, and then we subject it to carbonation. Okay, this is and then subject, and then to characterize the aggregate that is produced from this concrete. Okay, that is non-carbonated. That means after the concrete is produced, after 6 months, we crush it. And this carbonated upon 1 bar carbonated 5 bar means we crush it and then carbonate under a pressurized environment. So we can test the property of the aggregates. Okay, this is the different particle size. Is less than 5. This is the fine aggregate. This is a bigger aggregate. Okay, this is normally we use for concrete. We can see the water absorption and also the 10% fine value is the most important in governing the characteristic of an aggregate for use in concrete. So again, you can see with the carbonation, we have some reduction in water absorptions, and there's some improvement, a very slight improvement in strength. Okay, but this reduction in water absorption is real important, because when we compare to natural aggregate normally have a 2% water absorption. It's a good material for making concrete, but when the water absorption is too high, the making concrete is not too good. Okay, it will induce many inferior property to concrete. So we can manage to improve the property by using accelerated carbonation. If you're using 5 bar, this is even better. And then this is very interesting. So when we're using this carbonation reaction, we can actually show there's some uptick of CO2. We can monitor the amount of CO2 that is taken up through this carbonation reaction. This can be up to a few less than 1% to 2%. So 2% uptake of CO2 is quite substantial, okay, already, okay. So this is in sense, okay, using this technology or as it were, can not only improve the property of the recycled aggregate, but also take up some CO2, okay. So we are interested in looking into the aggregate, okay, see what whether it is truly improved. Okay, this is the microstructure of the concrete. Okay, uncarbonated. You can see the normal calcium silicate hydrates. There are the calcium hydroxide. There are the crystalline phases. But after carbonation, it's all changed. You can see the morphology or the visually is changed. You can see the aragonite, not only calcite is formed, there's also aragonite is formed. Aragonite is another part form of calcium carbonate. Okay, and then you can see, okay, the porosity of the aggregate. The porosity of aggregate, this is the natural aggregate. This is the natural aggregate is very non-porous. This is the non-carbonated one. This is the carbonated one. You can see the pore actually is reduced by the carbonations. And then when we use this aggregate to make new concrete, okay, to make new concrete, compared to using the uncarbonated one, this is non-carbonated one, this is the carbonated one, and then making into a new concrete, okay, then we can see, okay, using 100% replacement of replacement of natural aggregate by recycled aggregate, we can see there's about 22% improvement in strength, and 13% of improvement in modulus, and also about 30% improvement in durability. This is total charge pass, means the resistance to chloride penetration, and also the porosity of the new concrete is about 50% reduction in the new concrete. So by virtue of using this carbonation reaction, okay, or treatment, we can improve the coarse aggregate. We are using the coarse aggregate for making this new concrete. Okay. So this we go back to this flow. Okay, after crushing and sorting, we produce this coarse recycled aggregate. But actually, we can actually improve the property of this recycled aggregate by carbonation. Okay, by using waste CO2, as well as it can improve the property as well as capture some CO2. And this is applied also to the fine recycled aggregate. This is fine, means less than 5 mm. But we are very interested in at the same time very interested in the recycled fine powder. And the fine powder is the most problematic for the recycling industry or for the concrete industry, because if you have too much fine material, it cannot be really used in concrete because the fine material actually is treated as a contaminant in making concrete, because the silt take up a lot of water, making workability very, very difficult. Okay, and this is the most problematic material. Okay, so we are trying to develop a method, and this is really innovative. This is the first in the world, I would say. Okay, we have already patented. Okay, and what we are trying to do, this is done in a laboratory scale only. Okay, we are hoping there's some investor outside, okay, from the university can take it up, okay, to scale it up, and then to use it to produce some value-added product. Okay, so in the laboratory, what we have done, okay, this is the recycled fine powder. Mainly, this is cement powder, hydrated cement paste. Okay, of course, there's some contaminant, of course. Okay, but mainly recycled cement paste. So in the lab, we use cement paste as a simulated, okay, powder. Okay, we put it into a beaker, and then it's a large beaker. And then we add water. Okay, and then add the sodium carbonate. Sodium carbonate is a source of carbonate. Okay, and then with a stirrer, it will chemically react. Okay, we add a catalyst. Okay, and then there are some reaction, and then you can start to see there's some precipitate form on the bottom of the jar, and that is calcium carbonate. Okay, and that because there are a lot of calcium in the recycled fine. Okay, you can see. Okay, the recycled fine actually contains calcium hydroxide and then calcium silicate hydrate. they are the source of calcium. And this calcium will react with the carbonate from this sodium carbonate source will form the calcium carbonate. Okay, and then after filtration, and the calcium carbonate will be removed from the rest. Okay, this carbonate we'll look at it in more detail. Okay, soon. Okay, and then filtrate. And then the filtrate, what does it contain? The filtrate contain mostly silica, because in cement, okay, it's a calcium silicate. Okay, cement, the raw material of cement is calcium silicate, and also there's some calcium aluminate, but the most major chemical is calcium silicate. But after removing the calcite, there's still silicate. So the silicate, okay, is dissolved because at high pH is dissolved. Okay, so after we have obtained this silicate solution, we inject CO2. This is the second step carbonation. This CO2 could be from a waste source, okay, from a flue gas, okay. 20%, 30% CO2 is good enough. And then after some time, after injecting CO2, after some time, there are precipitate forms, okay, and this form is in the form of a gel. And then after removing in this particular case, we use centrifugation, okay, like something, and then separate the gel from the filtrate, and then we'll look at the gel again, okay, to see what it is, okay. So basically, okay, so we call a life cycle. This is we call a mass balance analysis, okay. We start off with a powder of 1 gram, okay, 1 gram. We've done it in a laboratory, so it's a very small scale. But in this 1 gram of material, it contains, okay, certain amount of calcium oxide. We've done it through, okay, our equipment, okay, it's XRM. Okay, this is a lot of calcium oxide. There's some silica oxide. There are very little of aluminum oxide, and there's some other impurities as well. Okay, and then after we conduct step 1 carbonation by the sodium carbonate solution, we produce a calcium-rich residue, and that is more than that of the original start off with 1 gram. We produce 1.04 gram of calcium-rich residue because we add a lot of CO2, calcium CO2 already here. So we are producing a lot of calcium-rich residues. Okay, and after the filtration, the step 2 carbonation, we add CO2, and then we're producing a silica-rich residue. It's about 16 or 0.165 gram. Okay, so all in all, we are producing more material than the start off with. Okay, but we are producing 2 material. One is a calcium-rich residue. One is a silica-rich residue. And then the filtrate, which is very interesting, is majorly is return back. Because we add here, okay, sodium carbonate solution as essential start off chemical. But after all this processing, we come back with the sodium carbonate solution, so it can be recycled actually. Also, there are no wastage. Okay, so we are trying to understand the influence of the concentration of sodium carbonate solution on this carbonation step, and then after the experiment, we know that okay, the paper, if you're interested, is already published, but this process has been patented already, okay, before the paper is published. So we found that okay, the concentration of sodium carbonate is does not need to be very high. And then how about the CO2 concentration? The CO2 concentration need to have, but do not need to be okay, pure CO2. So I don't know whether you know, okay, from landfill gas. Hong Kong have a lot of old landfills. They are managed by EPD. The landfill gas are collected. Some are collected to generate okay methane and for town gas purposes, or some flare. Flare means directly burnt. Okay, but all this flaring operation or the upgrading of the landfill gas will produce a waste gas, and this gas contains a lot of CO2. And this CO2, we believe it can be used for this carbonation purpose. Okay, and this, which is very interesting thing. We can use a waste gas from industry or from landfill to carbonate the material. And then we found that as long as when we use the CO2 to lower the pH to a certain level, then there we start to see the precipitation of the silica. And then what are these materials then? There are two, okay? We start off with powder, okay? We call RCP, recycled cement paste, okay? Recycled cement paste. And in the cement paste, actually, it's the hydrated phases. There's calcium silicate hydrate cannot be seen by XRD. This is X-ray deflection. I'm afraid this is a bit scientific, but this is what we detect phases in our powder. And there are the pollandite, okay, it's crystallized, the calcium hydroxide, they're unhydrated phase, okay? So we can see, okay, after the carbonation reaction in the calcium-rich residue is almost pure calcium carbonate, almost pure calcium carbonate, okay? And then in the silica-rich residue, this is no peak, but it's purely amorphous, which is a silica-rich gel, okay? So we can obtain two products from a waste recycled cement paste to obtain two products. When we look into it by a microscope, which is a scanning electron microscope, similar to the previous presentation by Mr. Lim, and we can see, okay, the calcium really are very small. Okay, this is the calcium. And then this is 2 micron, that is about, okay, less than 0.1 micron, okay, less than 0.1 to 0.2 micron size of this calcium, okay? And this is, we call nano calcium. Nano calcium carbonate, which is very good material for using in the concrete industry, okay? And this is the silica we produce, okay? It's not pure silica gel, it's not pure micro silica, but you can see the size is very small. Actually, it's nano size. It's nano size. So it could be used as a nano silica-like material. So what is this silica? We conduct a more extensive test we call solid state MMR to look into what is the molecular structure of this silica, and then which is quite similar to water glass. So water glass, you can see sodium silicate, okay? And then which is not 100% amorphous silica. This is amorphous silica, okay? And this is our material. So it's because it contains aluminum, so it's not pure nano silica as it is used, but it still contains some nano aluminum silica. And then we can have developed step to purify it in the laboratory as well. And then we have also patented that. Okay, so come back to conclude my talk. Okay, we have a demolition activity. We produce waste concrete. After crushing, sorting, if it's not going to the public dump or using a free reclamation with a low end use, we can really use for recycled material. And when we use this recycled material, we can produce value-added material through carbonation. For the coarse recycled aggregate, we can make it into a better aggregate through carbonation. For the very fine powder, we can make it into very high value added material we call nano carbonate as well as nano silica. Okay, so to conclude, accelerated carbonation not only turn waste into resource but also capture CO2. Okay, and then I need to acknowledge the funding support is not from commercial, it's all from the government or the construction CIC, and we hope to look forward because we want to commercialize this, and then we hope there are some interested party in Hong Kong. I especially look forward for investors in Hong Kong to commercialize our technology. Thank you very much.